Auzubillahi minash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum, dear students. Today we are going to learn about the vertical stresses in soil. That is lecture number 10. In today's topic, will start with the stresses in soil and stresses due to the self-weight plus water present in the soil, stresses due to the surcharge loads such as point load, line load, and uniformly distributed vertical strip load, uniformly distributed load by the circular area, and uniformly distributed load by the rectangular area. As you can see here, this is the ground surface, and here we are having the water table in the soil. Before the construction of this house, there will be geostatic stress or the vertical stress, the vertical overburden pressure will be exerted onto this soil element at a depth h, and that geostatic stress is acting due to the self weight of the soil layers which is present here. There will be some horizontal stresses as well, which are usually equal to the coefficient of lateral earth pressure into the vertical stress. But when you are constructing a house, you are adding a load such as buildings and other types of structures as well, embankments, railway track, that will cause the increase in the stress due to the loads or surcharge loads. So we are going to learn about the vertical stresses, how we can calculate the vertical stresses in soil, and also the stress increases due to various surcharge loads such as point load, line load, strip load, circular and rectangular area loads. Now, construction of a foundation causes changes in the stress, usually the net increase. We can call that as delta sigma. The net stress increase in the soil depends on the load per unit area, Q by A, to which the foundation is subjected, the depth below the foundation, depth of the foundation at which the stress estimation is desired, and several other factors which will be discussed in the foundation engineering as well. It is necessary to estimate the net increase of the vertical stress in soil that occurs as a result of the construction of a foundation, so that we can find out the settlement of that particular soil. So vertical stresses, then delta sigma, are used to find out the settlement in that particular soil. Those net stress increases, estimation of the vertical stress increase in soil caused by various types of loading, are based on the theory of elasticity. Now, soil is assumed as elastic, isotropic and homogeneous material in order to solve it by the theory of elasticity. Although natural soil deposits in most cases are not fully elastic, isotropic and homogeneous materials, calculations for the estimating increases in vertical stress yield fairly good results for practical work. As we already know, that soil is not elastic, not isotropic, and it's not the homogeneous material, but still it will yield fairly good results for the practical reasons. Three types of stresses are possible in soil mass: vertical stresses, lateral stresses, and the shear stresses. Only vertical stresses will be covered in this course. Vertical stresses are further divided into two types: vertical stresses due to self-weight of soil mass, and I will add water as well. Vertical stresses due to the external surface loads such as point loads, line loads, strip loads, rectangularly loaded area, and the circular loaded area. Now, vertical stresses due to self-weight of soil mass. They are also known as geostatic stresses, gravitational stresses, or overburden stresses. This is further divided into subcategory, which will be explained in the coming slides. For example, if we are having a ground surface here and we want to find out vertical stress or the total stress in a dry soil at depth Z, then we need to find out the unit weight of that particular soil, and we simply multiply it with the depth of this layer, and we will come up with the vertical stress due to self-weight of the soil. Now, if we are dealing with the saturated soil, and this is the saturated unit weight of that particular layer at a depth Z, so we will simply multiply the saturated unit weight with the depth of that particular layer to find out the sigma Z or sigma V vertical stress. Now, the total stress is equal to the effective stress plus pore water pressure. Now, the effective stresses are those stresses which are taken by the soiled solids or solid particles, and pore water pressures are those pressures which are generated in or which are taken by the soil, the water particles. This topic will be discussed in greater detail in geotechnical engineering 2, but for the time being you can note down that the total stresses are the stress which is taken by the soil solid particles will be effective stress, and the pressure which is taken by those water particles, if that pore water pressure U increases, this will disperse those solid particles, and the particles will try to go away from each other, go far away from each other, and therefore reducing the intergranular stress or the strength of the soil. Now, if we want to find out the vertical stress due to self-weight of soil mass for two different layers, one is the dry soil, the another one is the saturated soil, so we can simply multiply gamma into Z1 and gamma saturated into Z, but because there is no weight of soil which is acting over this CC layer, we need to also find out the total stress at BB soil layer, and you can see that we need to multiply that gamma with Z1, this depth. So if you want to find out the stress at this particular point, that would be the unit weight of this dry soil into the depth Z1. Now, if you want to find out the total stress which is acting on the layer AA, that will be gamma Z1 and gamma saturated into Z here. Now if you want to find out the pore water pressure, so we can simply multiply the unit weight of water with that depth Z, as Z1 is the dry soil, so we are using the depth Z. So total stress is equal to effective stress plus pore water pressure, and the effective stress is equal to total stress minus pore water pressure. We can also use the effective unit weight by subtracting the unit weight of water, which is equal to 9.81 kilonewton per cubic meter. Let's solve a simple example that we need to find out the total stress, effective stress, and pore water pressure at a point A, at a point B, and at a point C, that is the soil profile. The height of or the depth of the first layer is 6 meter. The depth of the second layer, which is a saturated sand, is 13 meter. The unit weight or the dry unit weight of the first layer is 16.5 kilonewton per cubic meter, and the saturated unit weight, dry gamma saturated, is equal to 19.25 kilonewton per cubic meter. As we already know that no soil particles or soil layers are present above the point A, therefore the total stress is equal to 0, pore water pressure is equal to 0, and the effective stresses are also equal to 0 at point AA. Now at point B, we will multiply the dry unit weight with the height or the depth of that layer, dry sand, 6 meter, and we will come up with the total stress, 99 kilonewton per square meter or kPa. Pore water pressure is 0 at point B, and effective stresses are equal to total stress minus the pore water pressure. Pore water pressure is 0, therefore the total stresses and the pore water pressure will be equal to the total stresses and the effective stresses will be equal to 99 kPa. If you want to find out the total stress at this particular point, so this will be the combination of the stress applied by this layer, the dry sand, and the saturated sand. So 6 is the depth or the height of the dry sand layer into gamma D, which is 16.5 kilonewton per cubic meter, plus 13, which is the depth of the saturated sand, and you will multiply it with the 19.25 kilonewton per square meter. Then this will be the total stress, 0.25. As we already know that pore water pressure is equal to gamma W into the unit weight of the water into that depth, 9.81 multiplied by 13 will give us 127.53 kPa. So we can write that 127.53 kilopascal. And if you subtract the pore water pressure from we need to write it a bit clearly. It's 127.25, and if you subtract 127.25, this will give us the 221.72 kilopascal. of the effective stress which is given here. Okay, that was all about the vertical stresses due to the self weight of soil mass and water. Now we are going towards the stresses caused by surface loads. Now the surface loads are external applied loads cause stresses in soil mass. At any point at depth z, the total stresses will be equal to the self weight and the externally applied loads. So that was the sigma v, and externally applied loads will is the stress onto that soil. Externally applied loads may act as point load, strip load, line load, uniformly distributed load in a rectangular area or circular area, or the combination of all. Starting with the stresses caused by a point load, Bosenisk in 1883 solved the problem of stresses produced at any point in homogeneous, elastic and isotropic medium. As the assumptions are very big, that the soil is homogeneous, elastic and isotropic, but the practical significance is there to make those assumptions. Now the point load is acting here P, and we are asked to find out the delta sigma z at this particular point or at this particular element. So an example of a point load is the vertical load transferred to the soil from electric power line or pole. We are asked to find out the delta sigma z at a depth z, but if you see in three-dimensional, this is the x-axis, this is the y-axis, and this is the z-axis. So this point or this element, if we are taking this element, and we are asked to find out the vertical stresses delta sigma. So this point lies at a distance of x and at a distance of y, and this is the resultant r which we need to find out to use this equation. So Boseniuk solution for normal stress at a point caused by the point load is given by the equation here, that is delta sigma p, which is the load, z is the depth of interest at which we need to find out the delta sigma or the stress increase, and this term includes the r, that resultant, which we can find out from the x and y distances. We can also call that term as the influence factor I. This is the influence factor which is dependent upon the resultant r and the depth of that particular element or point. A shortened equation can be written like this, and here this is the influence factor. If we are using equation, you can find out the r resultant. You already know the depth z, and you already have the information about the load P, and if you plug in those values in this equation, you can easily find out the stress increases. But if you want to use a figure where you can find out the influence factor, you can find out the r resultant by z, the depth. This is the z, and here it is the r, which can be find out using the Pythagorean theorem from the information or the values of x and the y distances. Then once you get the r by z, for example, we are getting r by z 1, then we can find out the I value, which is 0.084. You can also use table. If it's given for various values of R by Z, you will find out the influence factor. For example, for 0.10, the influence factor is 0.4657, and you can multiply that with P by Z square to find out the delta sigma. Consider a point. Now, solving an example, we will consider a point P, 5 kilonewton. This is 5 kilonewton. We need to calculate the vertical stress increase delta sigma Z at Z is equal to 0, 2 meter, 4 meter, 6 meter, 10 meter and 20 meters. So that Z is given for different depths. X value or X distance is given as well, that is 3 meter. Y value is given 4 meter, and we can easily find out the R value by using the Pythagorean theorem, and that R is 5 meter. Now we can use straight away that equation as well, and we can get for various Z values the delta sigma. For example, for R 5 meter, Z is 0, so R by Z will be infinity and I1 will be equal to 0. Now once that I1 is 0, delta sigma is 0. Now for the Z 2 meter, R by Z is 2.5 meter and I1 will be equal to 0.034, and we can easily find out the delta sigma is 0.043. Similarly, we can find these delta sigma stress increase values. We can also use the equation, this one, and we can also use the values of using the influence factor base figure as well, and the table as well to find out the influence factor. Assumption of a linear elastic mass. Use of the principle of superposition is applicable here when we are dealing with the 2 point loads, point load 1 and point load 2. Now, what is principles of superposition? That the stress increase at a given point in a soil mass in a certain direction from different loads can be added together. So here we need to find out the delta sigma due to these 2 point loads. Let's solve an example so that to understand the concept of principle of superposition. We are given with 3 points, or the point loads. Here at point A, the load is 2000 pounds. Here at point B, this load is acting, and at point C, 6000 pounds load is acting. This is the top view. This is the top view. We are asked to find out the stress increase delta sigma. We need to find out delta sigma at point D, but at depth 10 meter. Okay. First we need to find out the influence factor. How we can find out the influence factor? For example, this is the resultant. We need to find out the x and y values. So this is the x and this is the y value. R will be equal to 10 square, or we can say 10 square, 5 square plus 10 under root of 10 square. That will be equal to 11.18. Similarly, we can also do that for this point as well. Point B, this is the x and this is the y, and R will be equal to 11.18. And we can call that as RA and RB, and this is the RC from the point load RC. RC is equal to 5 feet. Okay. So RA, RB and RC values are given. You can find out the R by Z, and using figure table, or you can straight away put those values in that equation as well. You can find out the influence factor, and once you get the influence factor, you can find out the delta sigma. Here the notation is different, delta P, but this is the equation which you can use to find out the delta sigma. And the total delta sigma due to those three loads at A, at B, and C, we will get 20.2 pounds per square feet. This is a homework. A pole carries a vertical load of 200 kilonewton. We need to determine the vertical stress increase at a depth 5 meter. So we need to find out at a depth 5 meter. This is the depth here. This is the 5 meter depth directly below the pole and at a radial distance of 2 meter. Here we need to find out delta sigma, and here we need to find out delta sigma as well, due to this. Okay, so that's the ground surface, and we need to find out the stress increase at point A and at point B. So the answers are given here, that the stress increase here will be 3.82 kilopascal and the stress increase will be 2.63 kilopascal, using those figures, equations and tables. So you can solve this example at home. Now, stresses caused by a line load. The vertical stresses in a soil mass due to a vertical line load can be obtained using the Bosnisk solution. Now, the vertical line load can be of intensity Q prime, which is per unit length, Q prime per unit length along the y-axis, and this is the y-axis. So you can see this is the x-axis and this is the y-axis. Acting on the surface of a semi-infinite soil mass as shown below. Now, for the practical examples of the line loads are the loads from a long brick wall and railway track. You can see here that if you want to find out the delta sigma at a point A, we need to know this distance x at the depth at which, or the value of z. If we know this equation, and these are important equations to note down, that delta sigma z is equal to 2q, that q is the q per length, or you can say that this one, which is given q per unit length, or load per unit length. Value of x should be known, value of z should be known, and we already know that what are those x and z. X is the distance from the line of action of that q per unit length till that particular point where we are interested to find out the delta sigma z, and then c is the depth from the ground surface till that point. What is q? Q is load per unit length. If two or more line loads are acting on a surface, we need to calculate the effect of individual load, and we add them to find out the resultant effect on any point. We can use table as well to find out the delta sigma z divided by q by z, or we can use this figure as well to find out delta sigma z divided by qz, delta sigma z divided by qz, and that is for plus minus x by z values. Let's solve an example related to the two line loads on the ground surface. They are acting here. Q1 is 7.5 kilonewton per meter, Q2 is 15 kilonewton per meter. The x distance is 5 meter, and the x distance for the Q2 is 10 meter. The depth z is 4 meter, and we need to find out that delta sigma due to these two loads. Now we can use the concept of superposition principle, that we will find out the effect or delta sigma due to the Q1 load, and then we will find out the delta sigma due to the Q2 load, and we will add these delta sigma. This is delta sigma due to the Q1 load, 7.5 kilonewton per meter. We already know that x is 5 meter and z is 4 meter. Here z is equal to 4 meter and x is equal to 10 meter, and we will find out the delta sigma z by using this equation 2q cube of the z pi into x1 square plus z square into the whole of x1 square plus z square. Once we find out the delta sigma z1, that is 0.182, and we will use that equation to find out the delta sigma z2 as well by putting those values of x 5 meter and x 10 meter, z equal to 4 meter and z equal to 4 meter for two loads of Q1, and this is the Q2. So we'll find out that the total stress increase will be equal to the 0.227 kilonewton per square meter. At this point, this delta sigma 0.227 kilo Pascal. Now, stresses caused by a strip loading, for example, the stress at a point X, and this is the point X, due to the uniform pressure. This is the uniform pressure which is exerted onto the soil surface. on a strip area of width B, and you can clearly see in line load B is equal to 0, but here in strip loading B value is there. And an infinite length are given in terms of angles alpha and beta. What are those alpha and beta? You can clearly see that this is the vertical stress increase line, and here we are having the right corner of the strip loading. So the angle between this sigma z, or the delta sigma, which we need to find out, this line, this angle is beta, and the angle between the left corner of the strip footing and the right corner, this angle is alpha. And please note down that those alpha and beta values are in radians, and the practical example is of a magnet. So this is the equation which you can note down to find out the stress increase, where you need the uniform pressure, that Q value here, alpha and beta values in radians. That's it. You can find out the delta sigma. Now, in case of strip loading, this is the stress increase. This is the pressure which is exerted here. Now, if we are asked that what is delta sigma in here, that would be 0. But if we are asked that what is the delta sigma value, that might be equal to 0. But if we are asked to find out delta sigma value just beneath this uniform pressure, this will be equal to delta sigma. Or we can say that it's 100% of that Q value. But as we are going below this soil layer, maybe we will reach to a certain point. For example, Z is equal to 6.5 B. If that Z is 6.5 B, this load, this stress will be equal to 0.1. So we need to find out the depth Z, that at what depth we are going to experience the 10% of the stress increase. So if we take beta is equal to minus alpha divided by 2, and that is due to the direction of the angle here, as you can see here. Previously that beta was positive in this direction, but if you take beta here in this direction, this beta will be negative. Then 0.1 Q, we need to find out the Z, so we can change this alpha values into the degrees, because these are in radians, and we will find out that alpha is equal to 9 degree. Then we can use the trigonometry, basic trigonometry here, that the tangent alpha by 2, this is the alpha by 2, is equal to the b by 2 into z, which is the perpendicular by base for the tangent there, and perpendicular is b by 2, perpendicular is b by 2, and that divided by z, z is the depth, that now if you want to find out the Z, if you simply use the calculator, you can find out that the depth Z, which is equal to 6.5b, at 6.5b we are going to experience 0.1 Q, or the 10% stress reduction. Now stress is caused by a circular loading. The loads applied to a soil surface by footings are not concentrated loads. These are usually spread over a finite area of the footing. It is generally assumed that the footing is flexible and the contact pressure is uniform, which will be discussed in greater detail in foundation engineering. In other words, the load is assumed to be uniformly distributed over the area of the base of footings. Now we can use this equation to find out the stress increase if we want to find out the delta sigma beneath any point or even away from that line of action or the center of the uniformly loaded circular area. If we know the radius of that circular load, this will be the R, and this is at any particular point. If you want to find out the delta sigma, R will be equal to R, but if we are finding just beneath the center, R will be equal to 0. We can use figure as well. For example, if we find out the d by z, and d is the diameter of the circular load. For example, if we get the d by z value of 2, so we can say that the I value or the influence factor value will be equal to 0.65, and then Q is the uniform pressure which is exerted onto that circular area. Alvin and Ullery in 1962, they find out the increase in the stress at any particular point, for example here or here. If we know the R value, which is the radius of circular load, and that is the R, the distance between center and point of interest. At which we need to find out the delta sigma. If it's here, if it's here, and as I mentioned earlier on, R can be equal to 0 if we are finding delta sigma here, and R will be equal to R any value if you want to find out the delta sigma at this particular point. So you can use the delta sigma equation. Q is the pressure, A prime plus B prime, and A prime and B prime are the functions of Z by R and R by R, and that Z is the depth of that particular point. So we can use two tables. A prime values can be found out from a table 10.7, and B prime values can be found out from the table 10.8. As you can see here, various values of Z by R are given, various value of R by R are given. These are the values of R by R, these are the values of Z by R. For example, for the Z by R value 1 and the R by R value 0.2, what is the value of A prime? So that is the value of A prime 0.28763. Now if we are asked that what will be the value of the B prime for the Z by R value of 1, and if we are having 0.2 R by R value, and here is the R by R value, this is the value which we are going to get for the B prime. So we can solve an example related to it. So the R value is given 3, that is the radius of the loading. Uniform load Q is also given, is 100 kilopascal. We need to calculate the increase in vertical stress at depth of 1.5 meter, 3 meter, 4.5 meter, 6 meter, 12 meter at R is equal to 0 and R is equal to 4.5 meter. So at various depths we need to find out the delta sigma, and these depth values are already given. So we can use a table, we can construct a table depth for 1.5 meter, 3 meter, 4.5 meter, 6 meter and 12 meter, and we will find out the Z by R. For example, for the A prime, Z by R is 0.5, but as we know that R by R, or R is equal to 0, that was the case, the first case here is that the R is equal to 0, and we are finding the delta sigma beneath the center of that circular load. So R by R is equal to 0 and Z by R 0.5. So Z by R 0.5, R by R 0, that's 0.553. That's 0.553 is the A prime value. That's good. Now we will go to the 10.8 table for 0.5, Z by R and R by R is 0. So here we will see that is the B prime 0.358, 0.358. So you can use 10.7 table for the A prime values, and you can use 10.8 table for the B prime values, and you will find out the delta sigma using this equation for the 1.5 meter depth, 3 meter, 4.5, 6 and 12. And you can calculate those delta sigma stress increases for the R is equal to 0 case, that is the part A. Part B, R by R is equal to 1.5 meter, then you will use the 10.7 table for A prime and 10.8 for the B prime, and you will find out various values of delta sigma at varying depth 1.5, 3, 4.5, 6 and 12 meter. So that was the vertical stresses below the center of a uniformly loaded circular area, and even away from the center as well, because the R value was 4.5 meter. In case of the rectangular loaded area, you need to note down an equation that delta sigma, stress increase, is equal to the Q into the influence factor. That Q is the uniform pressure which is exerted onto the rectangularly loaded area, and I is the influence factor. We can use this figure as well, and you can use these complicated equations and lengthier equations to find out the stress increase beneath the rectangularly loaded area at any corner below depth Z of rectangularly loaded area. You can see here that the influence factor can be found out from the M and N values. And what is M? M is equal to P by Z. And what is B? P is the width of the rectangular footing, and L is the length of the rectangular footing, and Z is the depth at which we are interested in to find out the delta sigma. So you can note down this equation to find out delta sigma. And now if we are interested to find out the stress increase below the center of a rectangular area, so you can use this equation where I influence factor is dependent upon the M1 and N1, where M1 can be find out from the length by breadth ratio and N1 can be find out by the depth divided by the b, small b, and that small b is the half of the b or the width. Now we will use another figure. I will show you that how we can find out the delta sigma at various different points. For example, at the center of the rectangle, at the side of the rectangle, or even outside of the rectangle as well. So if the point of interest is outside the loaded area, we need to extend the loaded area. We need to extend the loaded area to the point of interest such that the point become the corner of the extended loaded area, as we have done here. We need to find out the stress increase at that point due to the extended area. We'll find out the stress increase for that extended area for the whole rectangle, and from the total stress we need to subtract the stress due to the fictitious area, and that is the fictitious figure or area which is added. So let's solve problem related to the rectangular loaded area. So rectangular concrete slab 3 meter by 4 meter. So this is the 4.5 meter length and 3 meter width. It's a top view. The width is 3 meter. So that's 3 meter. And that load Q is equal to the 2025 kilonewton. We need to determine the vertical stress increase at a depth of 3 meter at point A, at point B, and at point C, but the depth Z is equal to 3 meter. This is the point A, point B, and point C. Please note down that this point will be 1.5 meter from the corner of the rectangle. So this is the figure which you can use for finding the various values of influence factor, and this for finding the influence factor value we need to find out the M and N values. And M is equal to B by Z and N is equal to L by Z. So they are interchangeable, so don't worry about them as well. And then you can find out delta sigma using Q into I influence factor value. For example, M is equal to B by Z, and that for this point A we need to divide this rectangle into 4 equal points such that this point A will lie beneath the 4 corners of the rectangle. This is L, which is equal to 2.5 meters, so L by Z, and Z is 3 meter. L is 2.25 meter. B is equal to 1.5 meter, as you can see in here. So you will find out the M and N, and from the figure, this one, M is equal to 0.5, M is equal to 0.5, and N is equal to 0.75, here 0.1 2 3 4 5 6 7 8, so somewhere here, and n is equal to 0.5 here, and you can see the m is equal to 0, m is equal to 0.1. those curves are there, 0.2 3 4 and 5, so it's close to 0.11 in my case. From the book you can see that the value of influence factor is 0.107, and there is a typo here that its ID value is written 0.105. So in order to find out the pressure Q, so you can simply multiply and divide that load, which is 2025, divided by the area, and area is length into width or width into length for that rectangle, and this is the 3 meter into 4.5 meter, and that would be equal to 150 kilopascal. Now you already know that there are 4 contributing corners here beneath the point A. So if we multiply 150 into I, we need to multiply it with the 4, and that would be 63 kilopascal. Delta sigma value will be equal to 63 kilopascal. For the point B, as you can see here, we can divide this area into 2 rectangles in order to bring this point beneath the corner of the rectangle. M value is 3 by 3 because that is 3 meter, and N value is 0.7 because that is the width here, and here is the length. So length value is 3 and width value is 2.25. Now we are having M value of 1, N value is equal to 0.75, so you can use the figure to find out the I value, and that I value is 0.158. There are 2 contributing corners here. We already know that Q value is 150, so we need to multiply it with the 2 because there are 2 contributing corners to this point to increase that stress. Now for the point which lies outside the loaded area, one method is that you can find out you can take that rectangle here and bring that point beneath this corner of the rectangle. You can find out the M value. M is 5 because the length and the width values are 4.5 meter here and 1.5. I value will be equal to 0.22, so you can find out the delta sigma 1, and you can also find out the delta sigma for this fictitious area. For M value and N value, using the figure, you can find out the delta sigma 2 because this is the the influence factor is 0.13 from the figure. You can find out the from Q into I and Q into I1 and I2. You can find out the stress increases. Now what about the true stress increase? That would be delta sigma 1 from the delta sigma 2. We need to subtract this stress increase due to this fictitious area from area, or we can simply subtract the I1 minus I2, which is 0.22 minus 0.13. We need to subtract that, and we will find out that the net stress increase will be equal to 13.5 Pascal. Okay. We can also estimate the stress increase in the preliminary analysis of vertical stress increases under the center of the rectangular loads. The technical engineers often use an approximate method. It assumes that the influence of the load area spreads at 2, 1. That 1 is the horizontal distance 2 is the vertical distance or the depth of that layer, and that the same pressure is then distributed over the larger area. That larger area is represented by B plus C into L plus Z. Now this is the load which is exerted onto the surface, and at the surface, as you can clearly see, that MNC is equal to 0, delta sigma is equal to the Q into divided by area. Okay, so Q by A will be equal to the delta sigma. So at Z is equal to 0, delta sigma is equal to delta sigma. And as the depth is increased, this stress increase will decrease with the increase in the depth, and the approximate method is reasonably accurate compared to the cosmic elastic solution. To note down this equation to find out the stress increases due to the slope 2-1 method. Now, what are isobars? Are the pressure bulbs. An isobar is a curve joining points of equal stress intensity. What are isobars? Isobar is a curve joining the points of equal stress intensity. It is a curve or contour which connect all the points of same vertical stress. An isobar is a special curve shaped electrical bulb. The curved surface is symmetrical about the vertical axis passing through the point. So these are the isobars we are discussing here. The curved surface is symmetrical about the vertical axis passing through the load point. An isobar of particular intensity is obtained using basic equation for each loading type. So we discussed the point load equation, line load equation, strip load equation, uniformly distributed load for the circular area and for rectangular area. So all these equations can be used to draw the isobar, that particular load. Now, isobar of intensity can be drawn using basic equation for a point load, something like this. So delta sigma Z is equal to I Q by Z square, and in order to draw an isobar of 0.1 Q, so we can write that IB into Q by Z square, and that IB is equal to 0.1 Z square. Okay. So this is the isobar at which this Q will be equal to 0.1 Q. This point 0.1 Q, at this point 0.1 Q, and at this point 0.1 Q. So this is the sectional view. This is the point load, this is the soil. We can also draw this isobar, and for various value of IB, R by Z and R, isobar of any density can be drawn using basic equations as we discussed earlier on. For the strip loading, somewhat like these isobars can be drawn. But you can see here, these are the isobars. And for the point load, we can draw the isobars in somewhat these shapes. In multiple loads, are applied on a surface. As a result, their stresses combine with each other to enhance the load effects on particular depth Z. And you can see clearly that the Q here and the 3Q here, this is the stress increase point where the settlement can significantly increase due to the overstressing of that particular area. Such overstressing causes settlement of foundation of structure, tilting or overturning, as it happened in these silos. You can clearly see that tilting has occurred. Vertical stress distribution on a horizontal plan. Vertical stress distribution at a particular depth can be drawn using this equation for a point load, and as you can see at Z 2 meter, sigma Z is equal to delta sigma will be equal to IB into Q by Z square, and IB is equal to Q by 4, and that 4 is equal to 2 square. Various value of Q, and for various value of I, you can plot this Q at depth 2 meter. And you can see for different values away from the center or the line of action. So you can plot this distribution, that how delta sigma will change in the horizontal direction. So this is the delta sigma in the horizontal direction when Z is constant, and when the depth is varying beneath the point load Q. So you can see that the Z value will be greater, delta sigma value will be greater when it's closer to this point load. As we are going deep beneath the line load, the point load, delta sigma stress increase is decreasing, which means that when R is constant or equal to 0, delta sigma stress increase will decrease as we go along beneath the line load. So thank you very much. Any questions this lecture, you can go into the comment section. This is the end of the Geotechnical Engineering 1, which is the last lecture related to the vertical stresses in soil. It's about the vertical stresses and also the different types of loads there, surcharge loads like the point loads, line loads, and the rectangular loads, the area which is subjected to uniformly loaded area of circular loads. So I hope that you enjoyed our lectures so far, and thank you for immense support during this course. We have reached to approximately 12,000 subscribers during this course, so I really appreciate all the students and all the viewers that watched our channel. We will try our best to come back with the Geotechnical Engineering 2 lecture very soon. So till then, stay safe and stay healthy. Assalamu alaikum and Allah Hafiz.